All right, welcome to RISE Learning Machines seminars. RISE is Sweden's public research institute with more than 3,000 people working on a wide array of topics. The computer science department works on applied AI projects for the benefit of society, and we organize these weekly learning machines seminars. This meeting will be recorded, and if you want to be removed from this recording, let us know. And make sure to check out our impressive list of amazing talks that are collected on our YouTube channel. Today, I have the honor to introduce Johan Östman, who is a researcher at AI Sweden. Johan obtained his PhD in information theory in 2020 from Chalmers University of Technology under the supervision of Giuseppe Durici. His research interests include autonomous driving, privacy-preserving machine learning, and he's been collaborating with European Space Agency, AstraZeneca, Chalmers, and RISE. The topic of today's talk is the reality of federated learning from life sciences to finance and beyond.
Then thank you, Olof, for the presentation. And as Olof has said, I'm going to talk about federated learning. And I'm going to talk about it from the perspective of us at AI Sweden, which is this national initiative to try to accelerate AI usage within Sweden. And me, myself, I am a part of the team working on decentralized AI. And federated learning is, of course, a very central part of that. We're also looking into privacy-preserving machine learning, but in this talk, I'm going to mainly be focusing on federated learning. And at AI Sweden, as I said, we care a lot about bringing AI out to the ecosystem. So naturally, we interact a lot with industrial actors. And this is what this talk is going to be revolving around. Basically, the different federated learning projects that we have been driving with industrial actors and what we have learned and the research questions that is basically spurred out from those collaborations. And then we have brought those questions into academia. And we have tried to tackle them from a more theoretical or academical angle as well. So with that said, for those, let me just introduce first the people that are part of what I'm going to present. So at AI Sweden, this work has been joined with Edwin Callesen and Minuta Magal-Shrinat. At Chalmers University of Technology with Alexander Grali Amat and Javad Ali Akbari. And also Marvin Shemresi is working with us, and he's affiliated with the Technical University of Munich. And I'm also going to present a few applications that we have been working on towards the space sector together with European Space Agency, especially together with Gabriele Mioni, who is now at Delft, and Pablo Gomez, who was part of the Advanced Concepts team at European Space Agency. So with that said, I'm going to dig into federated learning now. And for those not familiar with federated learning, let me just give a very high-level introduction. So when we're talking about federated learning, it's all about collaboration. So let's look at the two extremes of training. Let's say that we have a bunch of clients, could be n clients. Each client sits on data. This data may be sensitive. It can be sensitive from a confidential viewpoint, and it can be sensitive due to the fact that the data is valuable. For example, if you are, let's say you are developing drugs and you are trying different components, you might not want those to leak to your competitors. So what you could do then is to perform local training. You basically have your data on-prem, you perform training when you want to develop a machine learning model. And the benefit of this is, of course, that the data remains confidential. Nobody can touch your data. Not in all cases, but the downside might be that you have a data set that is not good enough to provide you a model with high enough performance. Of course, you can then talk to your potential collaborators and pool all the data into a central place. And you can train a joint model on all the data, but of course, you let go of control of your data because you collect it in one single entity. So the question then is there something in the middle? And typically, we usually see that the more data you have, the better performance you get. So, if you train a model until convergence and you consider whatever metric, if you do local training, you expect to be performing worse than if you do central training. And what we're wondering then is, do we have something in between? And this was the idea that spurred the seminal paper from Google in 2017, where they looked at federated learning, where they basically take the best of two worlds. You gain access to a pool of more data, and the data remains confidential. And I will talk about what I mean about this. And the hypothesis then is, perhaps we cannot get up to the performance of central training, but we can probably do better than local training. So we should be falling somewhere in this area. This is the hypothesis of using federated learning. All right. So the objective of federated learning is to minimize some objective function. And we do this by looking at the, okay, so this I should say is called federated averaging, which is the most vanilla version of federated learning. And what we want to do is to minimize the summation across the same kind of loss function over the clients, weighted somehow, typically by the amount of data you have at the clients. And of course, these weights should sum to 1. And this loss function at the clients can be completely arbitrary, depending, it's context dependent, right? And the way we solve this problem is in an iterative fashion using gradient descent. So the server would broadcast the model, I call it WT here, at time step t. This model is basically the parameters of a neural network. At the client, we perform gradient descent on the local data, where this chi here basically denotes a random sample taken from the data set at the client. Once the client has performed gradient descent for a bunch of epochs, we return that model to the server. The server aggregates them according to this weighted averaging, and we repeat until we converge. This is federated averaging in a nutshell. And what really got me interested in federated learning was not really that you could start training on a distributed, you could start collaborating among different clients on heterogeneous data. I mean, distributed learning had been around for some time. What got me really interested in this was the fact that even if you have heterogeneous data, there are theoretical results that provide convergence guarantees. And this I thought was super cool when I started reading about federated learning in 2021. So basically, this is one of the results that kind of fascinated me when I dug into federated learning, basically stating that even if you have heterogeneous data at the clients, measured by how far away the average optimal is from the global optimal, you can still guarantee convergence at a certain rate, which is the number of training steps that you perform. And this kind of blew my mind. I thought it was really cool. So I started working on federated learning. And as soon as I started working on federated learning, I realized that this is actually super useful to a lot of different sectors. But the cool thing is that different sectors have very different challenges. So, for example, in pharma, we can collaborate with other companies in creating new drugs or discovering new drugs. Here, we are very interested in not disclosing any information of what we are working on at the given company, because this is very sensitive information, trade secrets. It might be compounds that you have not been able to patent yet. So you don't want this to leak. Whereas in other sectors, for example, in space, we might not care so much about privacy. We might care much more about efficiency, resource constraints, harsh environments, collaborating in making the model better because we're seeing different data with the satellites, for example. Furthermore, we can look at other sectors, say like finance. A very canonical example of the usage of federated learning in finance is for anti-money laundering. The banks, and I will talk about this more in the end of this presentation because we have a project on this, but basically banks, they can only see their own transactional networks, at least in Sweden. If you want to find money launderers and they launder money outside of your transaction network, this is a blind spot. So perhaps, and this has been shown, one could use federated learning to actually leverage information from different transaction networks in order to find these anomalies. And of course, there are a bunch of other sectors as well, like telecom. Ericsson is looking a lot into federated learning. In healthcare, we have Sahlgrenska University Hospital here in Gothenburg, looking at training models to perform diagnosis between hospitals. And also in mobility, we are looking into federated learning. So we are at the Sweden part of a project together with Volvo Cars and Sensect, where we are looking at fleet learning to not have to collect all the data in a central location, but learn on the fly out in the traffic. And this talk is going to focus on the different challenges in the different context. And when I say context, I mean basically the relations between the clients. So we're going to look at 3 different scenarios. We're going to look at a pharma scenario where we have co-opetition. We're going to look at a space scenario where we have what I would like to call internal collaborations. We might not care so much about privacy. We have the same organization owning all of the satellites, but we care about other things. And finally, I'm going to talk a bit about external collaboration, where we have entities that want to achieve a common goal, but not necessarily competing on the same topic. All right, so this is what my talk is going to revolve around. And I'm going to dig into pharma at first. So for this reason, I want to highlight a very cool project, I think. It was a European project in the IMI sector or group. And I think it stands for Innovative Medical something. And this was basically a federated learning initiative from 10 different pharma companies. So you see AstraZeneca here, which is very, very big in Gothenburg. You also see other very famous pharma companies like Janssen and Bayer. And the background is basically that bringing a drug to market is extremely expensive. And once you have a drug that you synthesize and you want to try it in clinical tests, you have a very high failure rate. So if we can filter out what drugs might be useful already at an early stage, there is a lot of money to save. And of course, machine learning is often used for this filtering because there are very subtle patterns that you want to find. And machine learning could be used, for example, if you have a compound and you can predict the toxicity, absorbability, you can basically attributes of a given component. But as data is very expensive to get your hands on, there's often a lack of data, and this limits model performance. So the hypothesis of the Melody project was basically, if we team up with other pharma companies, can we make these machine learning models that filter out potential drugs early in the process? Can we make them better? And the data that was used in this work was chemical compounds, their properties, and basically the outcome of various experiments, for example, toxicity experiments. And as I said earlier, data is considered a trade secret here. So it's very important that none of these companies actually get their hands on or even get to understand what components gave rise to a given test. And the data set consists of about 100 million measurements, and they perform data alignment via common pre-processing pipeline. So as these pharma companies are in co-opetition in this project, privacy is of utmost importance. And I'm only going to touch 2 of the things that they did in the project. And one of them is going to lead me into what I really want to talk about here. So the first one is that experiments and tasks should be kept private. You don't even want to disclose labels. And since you don't want to disclose labels, what they did in this project was to divide the neural network that you want to train into. So they call it a head and a trunk. The head is considered private. You don't want to share it with anybody. It's not part of the federation. The trunk, which is basically a model to create embeddings, is shared and federated. But still, you don't want anybody to even be able to perform, for example, membership inference attacks on the trunk. So except for that, they also looked into ways to mitigate those kind of attacks. Because when they did experiments on the trunk, they realized that it has about a 90% success rate to identify components that was used in the federation. But this is on a single model. So if we perform secure aggregation, basically looking at the aggregate of multiple trunks, and we try the same kind of attack, the success rate of the attack goes down rapidly.
And question, a component, is that a data point?
It could be a data point. So a component could give rise to multiple outcomes in an assay. So you can perform multiple tests on the same component.
Okay.
Yes, and secure aggregation is going to be a key part of what I want to talk about after the Melody project. So let's just go through the way secure aggregation works in a very basic fashion. So secure aggregation basically means that we don't want the server to see individual models from the clients. This is what we wanted to prevent, because the server could potentially perform a membership inference attack and understand what components or what chemical compounds went into the data. So in a nutshell, it's all about masking such that when we add the masks together, the masks cancel out. And this is the most vanilla version of a secure aggregation scheme. We basically communicate between 3 clients and we pick 3 random masks. We mask our models weighted with the number of data points that we have. And then, of course, when we add it together, the masks disappear and the server can only see the sum. Of course, when you want to do this in practice, you might not be able to agree on a randomness in the beginning, and then you might need to go through the server, and there are ways to do this as well via, for example, secret sharing schemes like Shamir secret sharing. But that's not important for what's coming up. All you need to know is secure aggregation prevents the server from seeing individual models. It only sees the sum of the model weights. Okay. So with that said, the results of the Melody project was a success. All of the companies that participated could see gains in the different tasks that was considered. So I should say that in this data, there were both data points pertaining to regression, there were data points pertaining to classification, and some kind of hybrid. And as you can see here, you have basically the different index of the clients here, and all of them gained except for this number 10, who actually got a little bit of worse performance in its model in the end. So 0 here means that you have exactly the same performance as before. And this is basically the relative improvements. But there is something that is very troubling from this graph. And that is that these bars are very different in height, which basically means that some companies gained more than others. And if you go to your boss and you pitch that, okay, we should do federated learning, we should invite all our big competitors, we should do federated learning. And then in the end of the project, you come back to your boss and say, yeah, I mean, we gained a bit, but the others gained much more than us. You're going to have an issue. This is kind of a career killer, I would say. So you don't want this to happen. And actually, so nobody disclosed exactly who gained what here. But after talking to people in AstraZeneca, I have understood that they have seen a correlation between how much data you provided with how much you gained. And there is an inverse relation, which is kind of intuitive. So you provide more data and you gain less, which is really not what you want to happen. All right. And also another thing that happened during the Melody training. So this, I should say, this was a big neural network that they trained, and it costs millions of dollars to train it. And initially, the first time they trained it, they realized that one of the clients had mislabeled some of the data points. And this caused the entire project to start over. They had to retrain the model, et cetera, et cetera. And the issue here is that it's very difficult to find out if you actually have somebody mislabeling or if the data is in any way poisoned when you use secure aggregation, because you have these two extremes that pull in different directions. Secure aggregation prevents you from inspecting individual models from the clients. But if you want to identify clients that actually deteriorate the performance, you want to be able to inspect them. So here you have a very nice privacy versus security trade-off. And with that said, the two important questions from the Melody project is basically, how can we guarantee fairness among clients? How can you make sure that you gain proportional to what you put in? And how do you identify model poisoning in a private way? These are the main two questions that I got out after being discussing with Astra about this. And we have dug into both of these questions together with Chalmers, University of Technology. And I want to present to you a paper that is going to be submitted to ICLR tomorrow, basically pertaining to the second question here. So how to identify model poisoning privately. All right. So private identification of malicious clients is what we want to achieve. We want to be able to tell what clients are contributing with bad data but we want to do it in a way that doesn't violate privacy completely for the clients. And in this endeavor, we're going to rely on a concept called group testing. And I find the history of group testing very interesting. So it was basically invented during the Second World War, because the US government, they wanted to test soldiers for syphilis. And it was very expensive and time demanding to test each individual soldier for syphilis via blood samples. So basically what they did was that they pooled blood samples together and they tested the pool of blood. And if any one soldier had syphilis in that pool, the test would be positive. If all of them had a negative sample, the test would be negative. So basically, in this case, we see here that the soldier who is sick is pooled into this group, and this test will come out positive, whereas the others only include negative soldiers, and we have a negative sample. All right. So we're going to use the same kind of methodology to try to achieve private identification of malicious clients. And when I say malicious, I mean, as in the Melody project, they don't need to be malicious on purpose. It could be that you mislabel on, accident, but it could also be that somebody is trying to inject data and, for example, performing a backdoor attack. So what we're going to do is we're going to replace the soldiers with clients. We're going to replace Uncle Sam here with a server. And we're going to have one of the clients that is malicious. It's going to perform either data poisoning or model poisoning, doesn't matter. All right, we're going to denote the true value of being malicious or not by D. And we're going to pool them into groups. And in each of these groups, we're going to perform a secure aggregation operation. So the server is going to have access to aggregate models of the groups, but it's not going to have access to the individual models. And then we're going to perform a test on the aggregates. The outcome is called T. And then we're going to use T to infer an estimate of the true vector D. And we're going to do this in a Neiman-Pearson way. So basically hypothesis testing between true and positive and negative. And these tests, as you say, can be completely arbitrary. So it can be composite tests. We can have multiple tests in a row. It can be based on a validation data set where you basically you take the aggregate model and you run it against the validation set to get some accuracy metric or recall or whatever. It could also involve spectral methods where you try to cluster some PCA components, for example, of the models that you receive. It can be basically anything. But you take the aggregate model and you get out a binary value, 0 or 1. All right. And the interesting thing about this is that this problem has a very close connection to channel coding, which turns out to be my previous field of study. And I will explain why. So if you look at this graph, it's a bipartite graph. In channel coding, we're working with bipartite graphs all the time. And the assignment of the groups can be expressed as a matrix. And this matrix is essentially a block code from communications. So basically what we can do when we design the group test is to pick a matrix A. And the way we pick it, or the design of the matrix A, will determine how many clients goes into each group, what is going to be the overlap between groups, and basically how many groups each client is going to be part of as well. And this determines the privacy and security in a very natural way. So if you have good distance properties from the channel code, that means that you are good at correcting errors. That's the same thing as having good identification in this framework. Whereas in the dual code, if you have a large minimum distance, which basically means that it's difficult to recreate one individual client, then you have privacy. So we can choose how we want to trade off privacy for identification by picking this channel code. And then we can use off-the-shelf decoding algorithms from the channel coding industry to decode this in an optimal way in this setting. So let me just show you the results that we can achieve with this. So this is a setting where we look at the ISIC 2019 dataset. ISIC 2019 is a dataset consisting of images of melanoma and moles and basically skin changes. We're looking at a setting where we have 15 clients. So this is a cross-silo scenario. And we are going to vary the number of malicious clients. And the hope is that once we apply federated GT, which is the framework, and we do the group testing, we can filter out the malicious clients and we can only proceed with the good ones. And in these experiments, I'm only going to do the group testing once. So I'm going to do the group testing in round 10. This is also arbitrary. I'm going to do the group testing in round 10. I'm going to find out, okay, these are the ones I believe are malicious. I'm going to discard them and then just continue with the training. We're going to use a model, an efficient net B0 model. And the tests that we're going to use in the group testing is basically looking at the accuracy on a small validation set consisting of 100 samples. And we're going to look at how far are the different aggregates from the maximum accuracy or the maximum recall. And this is basically the data partitioning in terms of labels over the different clients. So you can see that it's slightly heterogeneous as well. Okay, so these are the results. We are considering 2 attacks here. So we have one label flip attack where we basically turn a melanoma into a mole, which is I mean, from a medical viewpoint, this is a very severe attack. You don't want to, misdiagnose melanoma. And we are also looking at label permutation attacks where all the labels are just permuted by 1. We compare with an oracle that knows all the malicious clients, and also another private way to perform robust aggregation, not identification, but robust aggregation called robust federated aggregation. And it's based on the geometric median. All right, so as we can see here, if we have no defense, so this is the targeted attack, and the attack accuracy is basically how successful is the given attack. So how many times are we actually classifying melanoma into a mole? And you can see here that as the number of malicious clients grows, the no defense curve grows as well. So in the end, if we have 5 malicious clients out of 15, we have about 40% attack accuracy, which is not really good. If we have an oracle that knows exactly who is malicious and we remove them from the start, we are down at 20%. And if we use the group testing framework, we are actually performing even better than the oracle, because it turns out due to heterogeneity, some of the clients even deteriorate the model and are even, even though they're not malicious, they might even benefit the attack because of the heterogeneity. I mean, you can see these 2 clients, for example, that contain basically only 1 label. So this is something that it could both be considered a bug in the feature of this framework, that it's kind of difficult to tell when is a data poisoning attack occurring and when is it just due to heterogeneity. So this is something that we are going to look into in the future, but for now, we consider it a feature. Similarly, for permutation attacks, we see that if we have no defense, model performance deteriorate a lot. If we have an oracle, we go down to about 58% from 64 if we have no malicious nodes, and the group testing framework is basically on top of the oracle.
Can this framework handle different fractions, different numbers of attackers? What if 80% of the nodes are malicious?
Yes. So the important thing, as we talk about in the paper, is that at least one of the groups in the group testing consists of benign nodes. Mm-hmm. If all of them consists of malicious ones, then you're going to have a hard time. But if you have at least one group consisting of only benign nodes, you have the potential to, actually identify a lot of malicious ones. So in this setting, it depends on basically the realization of the malicious users in comparison to the assignment matrix. But 80%, I would say, is a very severe case. Then you probably have more serious problems.
Yeah. But this assumes there's no base model that is not contaminated in any way.
Yeah.
So essentially, this is from scratch.
Yeah. So the poisoning here occurs from the initial training round. So this is not like a malicious user turns on at the given round.
Yeah.
So this is also something that you could consider, and there is nothing standing in the way of applying this framework on this setting as well. It's just that we haven't looked into it. There is actually a paper called Flip from ICLR last year that argues that this is the most difficult type of attack to handle, when you always have the attacker present. But yeah, we don't have results on that, so I don't want to say anything about how we perform in that setting. Anyways, that's what I wanted to say about private identification of malicious clients. Yeah, if there are more questions or if you're interested, the paper is already on archive. And with that said, I would like to move on to the second topic of this talk, which is basically the topic of internal collaboration when we look at federated learning for space. So you have to excuse that this talk is going to be a little bit abrupt at times, but it's because I really want to talk about these different scenarios. I think they're really cool. All right, so federated learning for space. What is the motivation? Well, satellites in LEO, they collect a lot of data, and this requires a lot of storage and lots of communications if you want to send down the data to, for example, a ground station. Communications is something that is very difficult to come across in space because you have very, you fight for spectrum basically, and you only see your ground stations at very rare occasions. For example, if you look at this image here, which is coming from a packet in Python that I will introduce very soon, you see that a satellite here orbiting Earth in LEO can only talk to a ground station, I don't know, 5% of the time during orbit. So with that said, can we bring onboard learning to the satellite? Can we make it such that a satellite can utilize the data on board? It doesn't have to send all the data down to Earth. And can we actually train the machine learning model on top of the satellite? So doing inference on the satellite, this has been done for many years now. But actually training on board, this is kind of the next paradigm. So we wanted to basically look into the challenges here and see if this is even possible. So the hypothesis is that we can use federated learning here to boost the efficiency and the performance and make sure that we can train on board. And of course, the challenges are many. Some of them include that we are operating in a space environment that is very hostile. We have limited communication windows. And when we do federated learning, we want to keep communicating with the parameter server. But now we only see the parameter server at rare occasions. And this means that probably a global model that we started training from at one point in time will become stale at some point. So it's going to become old. And also, how can we handle the fact that we have limited resources? So we might not be able to upload a big data set on a satellite. We might not be able to run, a lot of iterations on a satellite because of battery constraints, etc. So can we somehow understand how this will impact the onboard learning? That's the question that we addressed. All right, so for this reason, we developed a tool called Paseos. Paseos is basically a Python framework that is very lightweight and designed for multi-agent simulation, where we are trying to model the important aspects of the onboard environment. So for example, we are modeling power constraints, radiation effects, bandwidth limitations, of course, astrodynamics, thermal management, temperature, and the communication windows, etc. And you basically can create one of these satellites, have them talk to each other in a given constellation, and run machine learning operations on top of this framework to kind of understand how these onboard environment will impact the learning. And just as an example from this paper here, we have a very much toy example in the paper where we try to showcase just how much these kind of environmental impacts impact the performance of machine learning. So here we have two satellites in a Sentinel-2 orbit. One of the satellites, so as I said, this is a toy example, but one of the satellites have access to this training data. The other satellites have access to this part. The goal of the satellites is to be able to classify a two-dimensional point into an inner or an outer circle. So this is the test data that both of the satellites will be evaluated on. So we run these two satellites in orbit around Earth. We'll have them communicate at first time after 10 orbital revolutions. So you can see here the test accuracy of the training on board saturates around 68%. So this is about as good as you get if you don't collaborate. Now, if you start collaborating, so each of these gray line is basically when the satellites communicate to each other. When they start collaborating, we see a big rise in the performance of the classifier, but there is a big discrepancy between these two satellites. So this discrepancy is not due to the actual model training. It's actually due to the environment in which the satellites are operating, because they are lying in orbit in opposite directions. And that means that when they share the models, one of the satellites will actually go into eclipse and will not be able to charge its batteries with solar power. And that means that effectively in each orbit, one of the satellites will only be able to train once until the battery is drained, whereas the other one can train twice. And that's the reason why you see this big increase for the blue curve, but not for the orange one. So even for this very much toy example, you can already see the impact of taking the onboard environment into account. And we wanted to take this one step further. So we started to look into, okay, can we actually apply semi-supervised learning in space? So the scenario is basically, we have a vague idea of what we want to achieve. We want to load a couple of, we have a limited set of data points that are labeled that we know that we want to classify into. And then we want to apply a semi-supervised learning approach on the satellites in the constellation to achieve a better machine learning model without sending the data down to Earth. And we're going to use asynchronous federated learning, where we basically apply a convex combination of the global model at the server and the local model, where we account for the staleness. And we are using the fixed match framework, which is a very famous framework in semi-supervised learning, where we basically train a model on the labeled data, and then we use that model to create pseudo labels from the unlabeled data. So in this case, we take an unlabeled data point, we create a weak augmentation, a strong augmentation, we classify it using our model, then we look at the logits, and if the model that we have trained on the labeled data is confident enough, then we say, okay, we believe that this is actually the true label, and then we're going to train the model against that as well. And we're looking at 3 different scenarios in this paper. So we're looking at a swarm scenario where each of the satellites is modeled using Paseos. And in this case, they can only communicate with their neighbors, but they can always communicate because they are in proximity. We're also looking at a federation where we have a ground station. The ground station is basically these 3 points in Svalbard, Matera, and Maspalomas. And we assume that they basically function as one ground station. So as soon as a satellite have a line of sight with one of these, they can interact and exchange model weights. And we also consider a scenario where we have a relay based on the European data relay system that is much further away from Earth, which basically means that the satellites can see it more often, so they can interact more often. We're going to look at the Eurosat dataset, which is basically a CFAR dataset for Earth observation. And we're going to load each satellite with 5 labeled samples only. So 5 labeled samples per class, that's what the satellites are going to start with. And then we have unlabeled data, and we're going to partition that between the satellites. So they have about 3,000 images per satellite. All right. So what we see here, when we run the simulation over 24 hours, which corresponds to about 14 orbital revolutions, is that it doesn't really matter which approach we use. If we use a federated learning setup with a ground station, a swarm setup, or a relay setup, we approach basically the same point. You can see here, it's very close, with the ground station as a relay being the best. We also model how much data we transmit, the power that we consume, the time each satellite spent on training, etc. But what's interesting here is that only using 5 labels per class, we're actually able to get up to about 91% at classification accuracy. And the interesting thing here is that we can even go further down when it comes to the number of labeled samples we have at the satellites. So this is another simulation that we ran where we only look at the swarm setting, this middle setting, and we look at the top one accuracy after running the simulation for 24 hours virtually. We have a centralized benchmark where you have all the data available. And we can see that we only lose about 2% from the centralized benchmark. If we run it in space, we take into account onboard constraints, and we do it in a decentralized way, which is quite remarkable, I think. And if we go down even in the number of labeled samples, you know, if we end up at 3, we are still performing at 90% classification accuracy. So yeah, that was kind of encouraging, I think. And this has led us to consider other scenarios as well, where we are basically, you know, starting from this paper, and we are looking into reconfigurable missions. Because if you can train a machine learning model to perform a given task within 24 hours, that opens up, you know, the door to reconfigurable missions. Imagine that you can have satellite as a service. You want to collect data, you want it to trigger on some way and send down data. So basically, you just upload a few samples of what you're interested in, and you have it trained for 24 hours, and then you have a machine learning model that can basically trigger on the sort of events that you're interested in. And of course, something that we have not taken into account here is that the satellites, they should gather data continuously. Right now, we just load all the data onto the satellites. We basically assume that the satellites, they have this data gathering phase where they collect all the data and then they perform training. But in reality, you might not be able to store so much data on the satellites. So it would be interesting to see what happens if you gather a small chunk, you do training, you throw that away, and then you gather a new one. So yeah, that's what we have been working on in the space sector on federated learning.
Just a question on that. So the sampling is random, I guess. So if it's non-ID, wouldn't semi-supervised learning kind of be a bit tricky in that sense if it's non-ID?
I would think so. I think so. We actually haven't tested this, and this is a very good point. That, you know, if you have one satellite that collects data over the desert and another collecting data in snowy environments,
yeah,
and you want to start collaborating, then of course you're in this domain adaptation regime where you might want to use other ways of merging the models than just, you know, this asynchronous approach that we used here. Definitely.
Thank you.
All right. Okay, so as I said, this presentation is a little bit abrupt in the corners, and this is all I wanted to say about the space setting that we have considered. And I want to jump into the final part where we are looking at external collaboration. And this is also a setting that is very dear to me, that I find super interesting, which is basically the scenario of anti-money laundering. So why would we even consider federated learning in anti-money laundering? I talked a little bit about it in the introduction, but let me explain a little bit in more detail. So we have a transaction network. People in the banks, they make payments to and from each other. And of course, within this transaction network, there may be users that perform money laundering. So they basically get illicit funds, and then they try to prevent anybody from knowing that these funds were illicitly obtained. And the UN has estimated that this is a big societal problem, basically standing for up to $0.8 to $2 trillion per year. And if one could actually identify this would be a very big step forward towards countering a lot of different crimes. But this is a very difficult problem. So let's consider this network, and let's assume that we have 2 banks in this setting. What happens is that once a transaction leaves the bank, we don't know what happens. And this makes it very difficult for individual banks to identify money laundering. And the way this is done today is basically that the banks, they have rule-based systems, basically if-else statements, and they have risk profiles on accounts given a KYC. And the false positives is extremely high, because from the bank's point of view, they want to make sure that they actually provide all the money laundering cases in case of FSA comes and knocking on the door. So what makes this even more difficult from an academic viewpoint is that there is no public data set. So from an academic point of view, the papers that are published are most often based on data sets that cannot be disclosed, because as soon as you disclose a data set, you can find out aggregate statistics from the data and know what is the average behavior of a user. And of course, if somebody who is performing money laundering knows the average behavior, you can adopt. So these data sets, you don't want them to be out there, which makes it difficult to even compare different approaches to money laundering. So the question is that we are asking in this project together with Swedbank and Handelsbanken at AI Sweden is, can we use federated learning for AML? And how can we tackle this fact that we don't have data? What is the time actually?
It's 15:47.
Okay. All right, so this is the pipeline, a general pipeline of how this works in reality. So we have an electronic surveillance system that alerts transactions. The alerted transactions goes to an inspector that inspects the alerts. And if that inspector believes that this is actually an alert, we create a case, we dig into it even further, and we may create a report out of it that is filed to the FSA. And the interesting thing here is that we have two competing objectives. So the banks want to limit the amount of resources they spend on investigating these alerts, because we have a very high false positive. And if the bank spend a lot of money on investigating one of these false positives, this is resources that could have gone to other things. Whereas the FSA, of course, wants to find all the money launderers, and they want us to improve the true positives. So improving true positives could also be that we basically flag everybody. Then you would have a very good true positive. But yeah, so the banks don't want that. They want to inspect as few as possible, but they want to inspect the ones that are really suspicious. So we have two competing objectives. And as I said, we don't have a data set. So how do we compete? How do we comply with the data set issue? Well, in this project that we are running, we are basing everything on a framework called AML SIM from IBM in 2018. So basically what we are doing is that we're creating a transaction graph in Python. We have complete control over how we create this graph, basically how many nodes should we have, what is the node distribution, degree distribution, etc. And then we can inject alert transactions into this graph. And once we have created the graph with all these alert transactions, we start iterating in time, where each of the nodes, which is an account, can perform a transaction, and they are tied to different patterns. And if they're part of a money laundering patterns, they can perform illegal or illicit transactions. And this will create a big file of transactions, and then we use this to perform classification. We can inject a bunch of different patterns. So, for example, these are a few examples. So we have normal transactions, basically corresponding to licit transaction patterns. Forward, we have fan-ins, fan-outs, cycles, we have forward transactions. And then, of course, we have alert transactions that we can inject. And some of them intersect with the normal transactions as well, but we also have a few that are unique for alert transactions. And this is an assumption that one can say what they want about, but this is what we did to make this data set work for us. And what we are doing here is basically extending this framework to our specific use case, which is Swish. So we want to find money laundering in Swish, in the Swish transaction network. And this is the reason for this is twofold. The first is that the banks have very different features when it comes to money laundering and the customers. And if you would actually apply this on like arbitrary transactions, you have an alignment problem. But Swish is such a new mobile payment system, so the banks have not really had so much time to tailor the features. So they look pretty similar among the banks. So this is the first reason. And the second reason is that we have aggregate statistics from the Swish network. So Swish is this collaboration of 12 banks that provide this mobile payment system, and they every year publish graphs like this. And we can use these graphs to create transaction networks that kind of, align or comply with the aggregate statistics to at least make sure that we somewhat follow realistic assumptions. And we have built this engine to mimic Swish, and we have created this visualization tool to see what these data sets looks like. And I should say that this is a project that's been going on for about 7 months, so we are in the middle of it. So our results are not that exciting yet. But basically what you see here is the transaction network, where we have created bank accounts according to how many customers there are in the Swish network in different banks. We can see all the degree distributions, etc. And you can see here that we have a lot of transactions going between banks. So the hope is that we can actually leverage these transactions between banks in a federated environment. And we have some preliminary results where we have started doing federated learning on top of this in a sandbox. And what we're seeing right now for this very specific small neural network, this is logistic regression only. But we see that for centralized learning, we have a recall of about 70%. And if we do federated, we converge faster, but we don't get as good performance as the centralized version. And if we do it in isolation, we have a small gap to the federated. But as I said, these are results that we haven't really spent a lot of effort on generating. So in the upcoming months, I hope that we can improve this significantly by using particularly graph neural networks. So with that said, I wanted to just summarize basically this talk. So I wanted to highlight that federated learning in itself is perhaps not super exciting from the federated averaging viewpoint. It's kind of you have off-the-shelf methods that you can just throw at a problem, and federated learning usually works. The interesting part for me, at least, comes when you want to apply this in practice, because you have very interesting problems that arises from the collaboration that are not solved. So as you recall, in co-opetition, in pharma industry, for example, risk mitigation and contribution scoring is very important. The contribution scoring is basically I would consider it a deal breaker if it's not solved to be used in competition. And defense mechanism that do not violate privacy is key. And we have looked in this direction to at least take one step further to be able to identify malicious nodes. When we have internal collaborations, we consider very different challenges. And here it's more about efficiency in resources often. So in the space setting, we care about converging fast. We want to use our resources in an efficient way. As I said in the beginning, we have this project together with Volvo and Sensect as well, where we look at fleet learning in cars. Same story. We care a lot about resource efficiency. And if we look at external collaborations, for example, in the bank sector, when we do money laundering or anti-money laundering, or in the healthcare sector, for example, if you want to perform, if you want to collaborate on training models on rare diseases, we care about privacy, because often here legal compliance is paramount. And there are so many interesting use cases for cross-sector collaborations in federated learning. It's just amazing. And with that said, I think I conclude.
Thank you. Let the questions begin. And in the space case, you mentioned some of the limitations in resources. But what kind of resources did you assume? Like what power consumption and what?
So we actually we had access to a Unibap device. So they have these hardware SDKs basically that mimics what actually goes into satellites. So we had access to one of those, and we measured the power consumption when we were training on top of one of those. And we actually ran Paseos. So we emulated the onboard environment on top of it as well. I don't remember the exact numbers, but they are in the paper if interested. But yeah, we tried to keep it as close to reality as possible without actually putting it up in space.
Yeah.
We actually went to one conference. I didn't, but one of my colleagues did, and the feedback was basically, I mean, it's cool and everything, but come back when you have it in space.
Yeah.
So yeah.
I guess, are there studies on sort of the effect of radiation, for example, on the computers?
So this would basically mean you're thinking about like bit flips and so on. Yeah. I'm sure there are, but I have not dug so deep into it. But of course, this is also very interesting to understand, what is the impact of severe radiation. It's we are modeling it to some extent, but we are modeling it basically using Poisson distributions and random flips. But we didn't run explicit experiments on it.
Natural law.
Yeah. Yeah, I mean, there are a lot of things that can be improved in this Paseos framework, and we have master students coming in and that will do their thesis in conjunction with it from Delft, for example, where we're going to improve the communication link, for example, because right now we assume a Gaussian link, basically Shannon capacity, and you have atmospheric attenuation and so on that we have not considered at all, clouds occlusion and so on. So there are many things that we can improve, but this is an open source project. It's on GitHub. So if anybody is interested in contributing to this, we would be very happy.
Question.
Hello. May I ask a question?
Yes.
Yeah, I'm Eric Thalberg. I come from a company called Moduli. We do like machine learning consultancy and stuff. I was wondering if you know of any federated learning systems that are currently in production, and if you know of any learnings from actually deploying such systems.
Yeah, so deploying federated learning is also an important aspect, of course. In production systems, no, I'm actually not sure. I know a lot of POCs, but I don't know if anybody have it in production.
Haven't they been talking about the keyboards for?
Oh yeah, I mean that's a good example actually. Thank you. I mean the original paper from Google, they used it for text completion, and that's in production, I guess. Also, we have a company in Sweden called Scale Out that is a startup doing Fed MLOps. That their entire business idea is basically to provide enterprise grade environments to be able to have federated learning up and running, and we're actually using that in this anti-money laundering project, their environments. But yeah, I have never. So personally, I've never come that far as to go to deployment of these things. That's.
No, I can see the reason why I'm asking is I can see a lot of MLOps considerations here, and I understand why there's a startup doing that. Thanks for a very interesting presentation.
Thank you.
Yeah, so I was I'm not too familiar with federated learning, but what I was thinking about was in the anti-money laundering setup. I mean, you in this particular case you used supervised learning in some sense, and I think pretty much all cases I've seen of federated learning, they tend to use supervised learning. But for the anti-money laundering scheme, wouldn't something like anomaly detection be an interesting approach? So my question is, have you seen algorithms specifically for anomaly detection rather than standard supervised learning approaches in the federated scheme?
Yes. So this can be used, and a lot of people are using. I mean, I think the technique showing most promise right now in AML are graph neural networks. Then, of course, you can tailor graph neural networks to handle anomalies in a better or worse way. And I know there was a recent paper that is going to be published in NeurIPS this year, where they actually benchmark a continuation of this AML sim from IBM on different graph neural network architectures and demonstrate really good performance on it. So yeah, I think people are looking in that direction when it comes to anomaly detection.
Okay.
And so are we, I should say. But we are looking at it from a federated viewpoint. So we are basically looking at subgraph federated learning.
Right. But it tends to be all neural networks, I guess. So no of the more classical anomaly detection schemes.
Yeah, I think there is a consensus that these rule-based methods, they are simply not competitive with graph neural networks in this setting. And you really want to take the structure into account because, of course, this is an assumption in the data set, but this is an assumption that has been, if you look at textbooks on AML, this is all over the place, these kind of patterns. So if these patterns occur, then of course you want to account for the structure of the of the nodes, how they interact with each other. And graph neural networks, they take this structure into account in a very natural way. So I think this is the reason why you see so strong performance among them.
Yeah, I was more thinking, I mean, for anomaly detection about at least a few years back, it tended to be our encoders and stuff like that. So you do anomaly detection by reconstruction error.
Yes. Yeah, I mean, this I guess you can do. I haven't seen this explicitly, but I mean, the graph neural network basically just creates embeddings for each nodes, and then of course you can train an autoencoder on top of that.
Yeah.
So yeah, sure, you could try that.
Okay. All right. Thank you.
Cool. So thank you, Johan, for this talk and this discussion as well. Next week, we will welcome Professor Klaus Robert Müller from Technische Universität Berlin. Who's going to talk about AI for the sciences. We'll come back in 1 week.